Hello dear students, welcome to mathematics class. This is Prakash from Tungal Degree College, Jamkandi. In this class, let us start with paper 2 of B.Sc third semester. So here let us discuss the syllabus of the paper 2. So here the title of the paper 2 is Group Theory, Integral Calculus and Differential Equations. So in this paper, now we are starting the first unit, that is Group Theory 1. So this unit consists of groups, abelian group, standard examples of groups, properties of groups, semi-groups, subgroups and its properties, then permutation group. So it is the syllabus for the first unit, that is Group Theory 1. Before going to start group, let us discuss some fundamental definitions required to group theory. So the first definition is set. A well defined collection of objects is called set. So here to define group, we need the definition of set. So here set is a collection which is well defined. So therefore a well defined collection of objects is called set. Then binary operation. Binary operation. So the binary operation means, in general we are denoting the binary operation as star. So here this star is the standard notation to denote binary operation. Now let us discuss the definition. If capital S is any non-empty set, then star is said to be a binary operation on the set S if for all A comma B belongs to S, then A star B belongs to S. So here it is the definition of binary operation. If S is any non-empty set, then the operation star is said to be a binary operation on the set S if it is satisfying the condition that for all the elements AB belongs to S. Here these two are the elements of capital S. Then after operating star on A and B, the product is A star B. That element also must be in S. Then only the star is called as binary operation on S. For example, there are so many mathematical operations: addition, subtraction, division, multiplication and LCM, HCF, there are so many operations. So let us discuss some examples which are binary operations and which are not binary operation on particular sets. So the first example is, so here it is the first example. Show that addition, subtraction and multiplication are binary operations on R, where R is the set of real numbers, but division is not a binary operation on R. So let us prove addition, subtraction and multiplication are binary operation on the set of real numbers. So to solve this one, let us consider the two elements A and B in the set of real numbers. So here A and B are the two elements in the set of real numbers. So the first one is addition. So here for all A comma B belongs to R, means for any two real numbers A and B, the binary operation is addition, that is a plus b. So, here we know that if you add any two real numbers, then their sum is also a real number. So, therefore, if a and b belongs to the set of real numbers, then a plus b is also a real number, that is a plus b belongs to R. So, therefore, it implies that addition is a binary operation on R. So, it is by the definition of the binary operation. So, in that definition, for all a b belongs to S, a star b belongs to S, then star is called as binary operation. Here in place of star, we are using addition, that is plus. So, therefore, addition is a binary operation on by this conclusion. Then the next operation is subtraction. For all a comma b belongs to R, let us consider the two real numbers a and b. Here the binary operation is subtraction, that is a minus b. We know that the difference of any two real numbers is again a real number. So, therefore, a minus b is a real number, then it belongs to the set of real numbers. Then by the definition of binary operation, we can say that subtraction is a binary operation on the set of real numbers. Then the third operation is multiplication. For all a comma b belongs to R, here a and b are any two real numbers, then after performing the binary operation, that is multiplication, then it becomes a dot b or a into b. So, here this product is also real, then it belongs to the set of real numbers, because the product of any two real numbers is again a real number, hence a into b belongs to R, hence it implies that multiplication is a binary operation on the set of real numbers. And then the last one is division. So, here we need to prove that division is not a binary operation on R. So, here division. Now, if a comma b belongs to R, means if a and b are any two real numbers, then here we are dividing a by b. So, here a by b is not defined, for b is equal to 0. So, if we take the value of b as 0, then we cannot define this a by b, hence that a by b is not the binary operation, because here a by b does not belongs to the set of real numbers, because if b is equal to 0, then we cannot define the fraction a by b, hence this a by b does not belongs to the set of real numbers, then it implies that division is not a binary operation on the set of real numbers. So, therefore, here we have proved that addition, subtraction, multiplication are the binary operation on the set of real numbers, but division is not the binary operation on the same set. Then let us discuss one more example. So, here it is the example. Show that subtraction and division are not binary operations on n. So, here capital N is the set of natural numbers. Here we need to prove these two operations, subtraction and division, are not binary operations. So, to prove this one, let 3, 5, here 3 and 5 are two natural numbers. Let us consider the two natural numbers 3 and 5. Then first one is subtraction. If you consider 3 minus 5, so here the difference of 3 and 5 is minus 2, and minus 2 is not the natural number, because minus 2 is the negative integer, and negative integers does not belong to the set of natural numbers. Hence, the difference of 3 and 5 is not a natural number. So, therefore, subtraction is not binary operation on the set of natural numbers. Then, if you consider the same numbers for the second operation, that is division, here if you consider 3 divided by 5, here it gives the answer as 0.6. Here 0.6 is also not a natural number, because natural number starts from 1, 2 up to infinity, but here 3 by 5 is 0.6 and it is not a whole number. So, therefore, it is not a natural number. Hence, division is not a binary operation on the set of natural numbers. So, therefore, here if we need to prove subtraction, division are not binary operations, then we can give any particular examples, but to prove the operation is a binary operation, then we have to prove the result in general values by taking a, b or x, y, like that. So, therefore, these are the two examples regarding the binary operation. Let us repeat the definition of binary operation. If S is any non-empty set, so here it is the definition. If S is any non-empty set, then star is said to be a binary operation on S. If for all a comma b belongs to S, then a star b must be in S, then only this star is the binary operation on the given set. So, therefore, this is the fundamental definition required for group theory. Now, let us start with the definition group. So, here group, a non-empty set. So, already we know about set. Set is a well defined collection of objects, and here we are considering non-empty, means that that set has at least one element. A non-empty set G with a binary operation, star is a binary operation, star is said to be a group if it satisfies the following laws. So, here a non-empty set G means G is having at least one element with a binary operation, star is said to be a group if it satisfies the following laws. So, here the first one is closure law. The first one is closure law. So, here the statement of this law is, for all A comma B belongs to G, means for all the elements of G, it implies A star B belongs to G. So, here if star is the binary operation on the set G, then to satisfy the closure law, here it has to satisfy the condition that for all A comma B belongs to G, it implies A star B belongs to G, means after performing the binary operation, its product must be in the given set G. Then second one, associative law. Associative law. So, here for all A, B, C belongs to G, to define or to statement, we require the three elements A, B and C, then A star B star C is equal to A star B star C. So, here in associative property, first we are operating star on the first two elements, and next we need to operate the same operation with the product of A and B is equal to A star. Here we need to operate the operation on the next two elements, they are B and C. Then third one is identity law. Identity law. Here the statement is for all A belongs to G, then there exists, it is the symbol of there exists an element, there exists an element E belongs to G such that A star E is equal to E star A is equal to E. So, here it is the statement for identity law. For all A belongs to G, means for each and every element of G, there exists an element small e belongs to G such that A star E is equal to E star A is equal to A star E is equal to E star A is equal to A. So, here we are operating the binary operation star on the elements A and E, then E and A, then the result must be is equal to the element A itself, then this E is called as identity element. So, that is E is the identity element of G. So, here the value of A will not be changed after applying the star with the element E. Then fourth one, that is inverse law. Inverse law. So, here the statement is for all A belongs to G, there exists an element A inverse belongs to G such that A star A inverse equal to A inverse star A is equal to E. So, here it is the law of inverse or inverse law. So, here for all A belongs to G, there exists an element that is denoted by A inverse belongs to G such that A star A inverse, here we are operating A to A inverse on the left side is equal to, here we are operating the same A on the right side, but the product will be is equal to E only. Here E is the identity element of the set G. So, therefore, here if a non-empty set G with the binary operation star satisfies the 4 laws. The first one is closure law, that is for all A B belongs to G, it implies A star B belongs to G. Then associative law, here we need to consider 3 elements, A B C belongs to G, then A star B star C is equal to A star B star C. Then the third one is identity law, that is for all A belongs to G, then there exists an element E belongs to G such that A star E is equal to E star A is equal to A. Then the last one is inverse law. So, here for all A belongs to G, there exists an element A inverse belongs to G such that A star A inverse equal to A inverse star A is equal to E, which is the identity element of G. So, if these 4 laws satisfied for a group or for a non-empty set G, then that set G is called as group. So, here if G is a group with binary operation star, then it is denoted as G star. If we write a set G along with the binary operation star in the same bracket, then it implies that G is a group along with the binary operation star. So, therefore, it is the definition of a group. The name itself indicates that if the number of elements in a group is finite, then it is said to be a finite group. So, here it is the definition. A group is said to be finite if it contains finite number of elements. Then the second one is order of a group. The number of elements in a group is called order of a group. So, here the number of elements present in a group is called as order of a group. Suppose if a group is containing 2 elements, then the order of the group is equal to 2, like that. The next, infinite group. A group is said to be infinite if it contains infinite number of elements. So, here if the number of elements is infinite, then it is the infinite group. Now, let us consider some standard examples of groups. Examples. The first one is G is equal to the set 1 and minus 1. So, here the number of elements in this set are 1 and minus 1. So, therefore, we can write that order of G is equal to 2, and this set is a group under multiplication. So, here the set G is equal to 1 minus 1 is a group under multiplication, means here we can write this as G cross. The set G along with the binary operation multiplication is a group. So, therefore, here means the set G is equal to 1 minus 1 will follow all 4 axioms or 4 laws which are told previously, the closure law, associative law, identity law and inverse law. They all satisfied by this set. Then second example, G is equal to 1 omega square is a group under multiplication. So, here this is the cube roots of unity. So, 1 minus 1 are square roots of unity. So, here this is the cube roots of unity, 1 omega and omega square. So, therefore, this set will also satisfy all the 4 laws. Then the third example is G equal to 1 minus 1 I minus I is a group under multiplication. So, here this is also a group under multiplication. So, here this set is 4th roots of unity. So, these are the standard examples of groups. The first one is square roots of unity along with the binary operation multiplication, then cube roots of unity along with the binary operation multiplication, and finally 4th roots of unity. So, here also it is a group under multiplication.